So what I'm going to teach you today is expansion lemma and its application. Okay. So how many of have attended the course and have seen crown reduction? All of you have seen crown reduction. Very nice. So as we'll see, it is going to be a complete generalization of crown reduction, or what is called, I hope all of you know what Hall's theorem is. How many of you know Hall's theorem? Do you know Hall's theorem? Do you know Hall's theorem? Yes, no? Please tell me. If you don't know, then I will tell. Fine, good. So I'm going to use both of these things and give you a kernel for, so the kernel which I like to give you is feedback vertex set. Component order connectivity. And we'll see some more if I have time. So, and I'm not going to follow the textbook, I'm going to follow my notes. So, how many of you have seen anything about feedback vertex set? Have you in this course? What do you know about feedback vertex set? So, what is a feedback vertex set? Feedback vertex set input is an undirected graph G a positive integer k, okay, and the parameter is k, and the question is, does there exist f subset of Vg okay such that G minus f is a forest, right? So this is the problem. So what all things have we seen about this in the course? Yes, no, have you seen anything about this problem in this course? What have you seen in this course? Then you have seen a kernel for, okay. So let's call this problem FVS. So you have seen kernel for FVS when input is chordal. Anything else? Which is basically nothing but triangle hitting set. Okay, what else? Have you not seen any algorithm? Huh? Okay. Log n to the power. Have you seen the degree sequence algorithm? No. Like I want affirmative answer, yes or no, not like maybe. Have you seen this degree sequence based algorithm? That runs in time k power k. Have you seen this in the course? Yes, exactly. This algorithm. Yes, no, no Diksha? Oh, you have not been attending the course, but you don't remember it. fine. Anyway, so what is our goal? Our goal is to design, what is our goal? So our goal is to design a polynomial time algorithm. What algorithm? A polynomial time algorithm that takes as an input g comma k and returns an instance g prime k prime. K prime will be less than equal to k. Okay. So so what is our goal? To design a polynomial time algorithm that takes the input g comma k and returns an instance g prime k prime such that what are the two properties? First, such that a g has a feedback vertex set of size. This f is also called feedback vertex set. Okay, or FVS in short. So G has a FVS of size k if and only if G prime has a feedback vertex set of size k prime, and furthermore what property we will have? Property will be have is that the vertex set of G prime is less than equal to order k square and H set of G prime is less than equal to order k square. So this is what our goal is, right? And this is nothing but this is called polynomial. This is called polynomial kernel. This is a definition, basically definition for polynomial kernel. Okay. So here's a problem. Here's the goal. Okay. At least for the kernel, I will use either I will prove to you or I will use the fact that feedback vertex set has a constant factor approximation algorithm, or I will give you another constant factor approximation algorithm, but for now let us not go there. Okay. So first let me define, so that is our goal. To achieve this goal, for now what we are going to do, we are going to get away from here and going to explore some combinatorial structures, which is what I call expansion lemma, and we will see proof for that, and then we will see how we are going to get them. Okay. Okay, so let me define a notion of Q star. What is a Q star? A Q star is this, a vertex V with Q leaves. So, we have a central vertex and we have Q leaves, degree 1 vertex. So this is like a Q star. Okay. And now what I am going to define is notion of what is called, okay. So basically you have one vertex of degree Q and all other vertices of degree 1 exactly equal to 1, okay. So this is a Q star. Now what I am going to define a notion of expansion. So what I am saying to say, let G be a bipartite graph with Vg being partitioned into A disjoint union B. So any bipartite graph you can partition the vertex set into two parts, A and B, okay. And what is the property? Okay, a set of edges M subset of Eg, okay, is called Q expansion is the following happens. What happens? Q expansion Q greater than equal to 1 if but let me see what it mean, Q expansion of A into B. This is important to remember, A into B if the following happens, okay. What is this? If every vertex of A is incident to or adjacent to, is incident with exactly Q edges of M. So there is a set of edges, it's called Q expansion of A into B if every vertex of A is incident with exactly Q edges of M, and the second property is, what is the second property? M saturates exactly Q, exactly how many vertices? Q times A vertices of B, okay. So this is what it is, M saturates exactly Q times A vertices of B. So how does it looks like if we draw a picture, okay. So I am going to rub this side. Okay. So now how does it look like? So basically if you think of this way, this is A and this is B, right, and M is some set of edges which are going across, right, and what is the property of M? Every vertex in A is adjacent to how many edges? Exactly Q edges. So let us say Q equal to 2. And now what is the second condition tells? M saturates exactly Q times cardinality of A vertices of B. So if it is 2, then how many vertices do I have? 1, 2, 3, 4, 5, 6, 7, too many to draw example. So let us make it smaller, 1, 2, 3, 4. Let us apply Q equal to 4, Q equal to 2. So how many vertices they saturate in B? Exactly 2 into 4, right. So if there are 4 vertices, so there are like 8 vertices, 4, 5, 6, 7, 8. And now what is the property? Is that every vertex of A is incident with exactly Q edges of him, right. So suppose they saturate this, now one guy is adjacent to 2 vertices because they are adjacent to, so suppose this is adjacent to this guy and it is adjacent to this guy. Now look at this guy, he is adjacent to 2 guys. Now can he be adjacent to these two, any of these vertices? Right, because then the budget that how many people they can saturate in B will go down, because then you will have a, so basically this is exactly what it is, right. So basically now he picks up other 2 guys, this guy picks up other 2 guys, right, and this guy picks up 2 guys. So actually what property is, if you notice, is that they are basically, if you look at these, so now if you look at this graph and look at this set of edges, just this set of edges, these are basically stars, they are like 2 stars, right, and they are pairwise vertex joined. What is the property? They are pairwise vertex. Look at this, right, look at this guy, look at this guy, look at this guy, they are all pairwise disjoint, right. So these are the certain properties to notice. What is the property? First, and another thing, like just let us name these guys, okay, let us name each of their edges the way you wish to. Let us call this edge 1, 2, let us call this edge 1, 2, 1, 2, 1, 2. If you look at just 1, all the edges which are 1, they are basically a matching that saturates A. If you look at the just 2 edges which are numbered 2, that is a matching which saturates 2, like that is which saturates A. So basically it is, in some sense, if you, this is why it is generalization of this, if Q equal to 1, it is nothing but it is a matching. For q equal to 2, it's a star where it's which I can construct maybe using twice matching, right. So basically there are two disjoint matching which are saturating this. When q equal to 100, there are 100 disjoint matchings, edge disjoint matching which are saturating these guys, like pairwise edge disjoint matchings. And since you are going to saturate here, automatically you are going to be vertex disjoint in the other side because this side you are fixed, right. So basically these are the property. So basically if you have a q expansion, then basically what it is, that basically there are q edge disjoint matching which saturates A. These two are basically equivalent concept. Okay, so this is how one should view them, right. It is nothing but it is set of edges which is formed by certain set of matching which saturates the left side. Okay. Okay, so now, that well said and done. Okay, so now what does Hall's theorem says? Okay, let's write down here Hall's theorem. What does Hall's theorem says? If you have a bipartite graph A and B, right? If you have a bipartite graph A and B, what does Hall's theorem says? Perfect matching? Okay, okay. So basically it says there exists a matching saturating A if and only if for all x subset of A, right, neighborhood of x is this, right. This is exactly what it is. Now I would like to prove a similar statement about q expansion, okay, right. This is exactly what is here, right. Now I told you what q expansion means. This is exactly what q expansion means. So what should we prove? What should be the theorem? Okay, so here's my lemma. Let G be a bipartite graph with bipartition A comma B A comma B, then there is a q expansion from A into B if and only if what? If and only if what? Think for a minute. Right? For q equal to 1, I have a certain statement, right. This is exactly, if I put q equal to 1, then what I have is nothing but a Hall's theorem, right. If I put q equal to 1, then this is nothing but a Hall's theorem, right. But q equal to 2 is not a Hall's theorem, q equal to 100 is not a Hall's theorem. So what is the right modification we must make to have a proper characterization here, right. So how do you go about making such a statement, right? I mean, if I have to be saturation, look, one direction of the proof is always trivial, right. So which direction of this proof is trivial? The direction of the proof which is trivial is this direction. If there exists a matching that saturates A, then clearly for any x subset of A, neighborhood of x is greater than or equal to A, because look at the matching edge which is here. This itself is at least as much as this set size, and there could be many more neighbors here, right. So this is an obvious direction. Now what will be that obvious direction here? And then the good part is trying to prove that obvious characterization, is that necessary characterization also sufficient, right? And if not, why it is not, and then you try to make modification while you are building a theorem, right? So what is this, right? Q expansion from A into B if and only if what? If and only if for all x subset of A, neighborhood of x should be what? That's it, right? Let's try to prove this. Whose direction is trivial, whose direction I shouldn't even try to prove, and I will not prove this. Forward direction is really trivial, because if there is such a thing, then you look at your x, each guy has a q neighbors which are disjoint, right? So this itself gives us q times cardinality of x, but there could be more drivers, right? So the forward direction is as trivial as it was for the Hall's theorem. What is not easy is a reverse direction. Let's try to prove reverse direction. Not that I remember, but let's see. Okay. Okay. Here's the hint. Let me see how many of you are wise enough. Okay, I want to prove the reverse direction. Okay. Okay, that's a good idea. Hold that thought. Do you have some color chalk?
No, no color chalks.
Hmm? Oh, we cannot use color chalk.
We can, but we don't have it right now.
Can you call these people to give you send us some color chalk? Okay, so let's follow the thought of what Diksha was saying. So what I'm going to do, given a G, I'm going to transform a graph, a transform to G prime. Okay, and what I'm going to do, I'm going to make a clusters. So B, I keep it unchanged. Okay, let me use it. Okay, so I'm going to rub this portion. Okay. So what is the transformation I'm going to do? The transformation which I'm going to do is basically, so there are many ways of looking at it. So think of this as B, and let's say Q equal to 2, right? Basically what you do, this is A and it had some neighborhood. Okay, here what I do, I make a copy of this graph between this and this, right? So basically suppose I had A1, A2, A3, A4 as the vertices. I again make A1, so let's call it 0th copy, or the first copy, I make second copy, and the neighborhood of this is same as neighborhood of this because I am not changing B. Similarly, I will have A22 who will have same neighborhood, and A24. So basically what I am saying is that, okay, for every vertex okay, A in A, for every vertex A in A, make q minus 1 copies, say A1, A2, A q minus 1, and how do we give adjacencies? Neighborhood of A is equal to neighborhood of A1, neighborhood of A q minus 1. So if A saw some particular two vertex, its copy also saw the same vertex. So basically it's like I have made q minus 1 copies of the same vertex. So what I have done, I have made left hand side graph, like I have bloated it up by q times. By how? By copying the neighborhood of each AI with q minus 1 new vertices. This is what I have done. So did you understand the transformation? Okay. So the transformation is everything. For every vertex A in A, you make q minus 1 copies and give him exactly the same neighborhood as its parent is. Okay, and that's it. So now basically we have a graph A and B, and we have a cluster of vertices. This is what I call cluster now. And what is the property of this cluster? Each cluster has size q, and they all see the same guy here, right? So think of this, that I have taken this here and put it here. Think of this, that I put it here, right? So like it's a cluster. Here, what is this cluster? This cluster will consist of A, A1, A2, A q minus 1. This is say B, it will consist of B, B1, B2, B q minus 1, and so on and so forth. That's it, right? And what is the property? The neighborhood is same. Okay. Okay. So this is how it looks like. Okay. Now I have to show that, what I have to show is that we are showing the reverse direction. This property holds in my original graph. Then I have to, what did I show? Then there is a Q expansion from A into B. So if there was a Q expansion, then this happened. Now we have to show this. Okay. Okay. So let's look at this graph. Okay. And here I'm going to show is that I'm going to look for a matching of size. So this is not A actually. It's like some A tilde, or right. It's A tilde comma B because I have copies. Now I want to apply Hall's theorem. So if there is a QX, if there is a matching saturating A tilde, then I'm going to claim to you, if there exists a matching that saturates A tilde B, then we have a Q expansion. If there exists a matching that saturates, okay, what, let me write it down. If there exists a matching that saturates, if there exists a matching that saturates A tilde, okay, A tilde, let's call this in G prime, then there is Q expansion from, then there exists a Q expansion from A into B. Why? Look, if there exists a matching that saturates, it means, look at all these guys, right? They are part, right? I'm only looking at the concentrating yourself on the, because there is a matching. So of course their endpoints in B are distinct because they are matching, right? But look at here. So for example, let's look at one example with Q equal to 2 and we will see what happens, okay? So this is very simple, right? This is basically, let's suppose this is a cloud which is going through, another cloud which is going through, another cloud which is going through. But let's go back in the old graph. They are the same vertex, right? Because this, why did I give this edge? Because there is an edge incident to him to this vertex. That is why this edge exists, right? So if I go back into my original graph and I collapse this to a single vertex, the parent vertex, then these edges are present, right? So there is a mapping of these edges into my original graph, and that is nothing but a Q expansion, right? So if there exists a matching that saturates A tilde in G prime, then there is a Q expansion from A into B, right? So, okay, so all I have to show, if it is not, then something goes wrong, right? Is that okay? Okay, fine. Okay. Okay. So suppose there exists a matching that saturates A tilde. It means it also saturates each of these clouds. So look at one guy's cloud. So here it is A and here it is A1. Let's go back to the original graph. How did you give an edge? What is the property of this? N of A is equal to N of A1, right? It means this edge is present in the original graph with A. So suppose this is B and suppose this is, how do I say, let's call it star and this is just circle. These are the two vertices in B. But what is the original graph? There is an edge from A to a star and there is an edge from A to a circle. That is why this is there. Now all I am saying to you, look at a matching here. Now for each blob, you just go back and take this edge not with A1 in the original graph. So what are you going to get? So basically this matching is going to be collapsing at A and it is going to give us what? Star. If I had a third vertex here, because it's a matching here, so the endpoints in the B side is definitely distinct, but since they are from the same cloud, it means when I collapse them to the parent vertex, all I am going to get is a star. And since it's a matching here, in the B side, every star's copies are going to be distinct, and that is why it is a Q expanse. Okay. So now, if there exists a matching that saturates A tilde, then there is a Q expansion from A into B. Okay. Okay. So all we need to do is to show this. Suppose this is not true, because if this is true, then we are done for the proof. If this is not true, what we will show? Then we will show that this condition gets violated. Okay. Suppose not. What does imply? It means Hall's theorem gets violated. It means what is the converse of this? There exists a matching saturating A if and only if blah happens, or the contrapositive, there doesn't exist matching if and only if there exists an X such that this happens in reverse, right? So there does not exist a matching saturating A tilde. It means there exists a X tilde subset of A tilde, X tilde subset of X tilde, such that what is the property? Neighborhood of X tilde is strictly less than X tilde. Agreed? Yeah, this is what property is. Now what I am going to do, look, first of all, I am not going to consider any X tilde. Look, if X tilde consists of these two vertices, there is no harm putting the third vertex also in X tilde, because they all have the same neighborhood, right? So every cloud has the same neighborhood. So we can assume that we can assume without loss of generality, okay? We can assume without loss of generality that if A belongs to X tilde, then all its copies belong to X tilde. Agreed? So this is the kind of X tilde we are picking, because neighborhood structure is not going to change, they have the same neighborhood. Great. Okay. What should I rub? Thank you. Okay. What should I rub? This. Should I rub this? Is it okay? Okay. So now clearly our objective is that take this and let's see what happens in the original graph G. So let X be the subset of Vg, or basically not even Vg, subset of A, such that X along with all its copies form X tilde, right. Now I have this X tilde in A tilde, so basically there is some parent set which with all its copies is equal to X tilde, right. So let us concentrate on that X. Okay, what is the property? Let us try to understand that. The property is neighborhood of X tilde is this correct? Right, because we never change the neighbor. Now what is this?
That is less than order of X tilde.
This is order of X tilde.
Here Q times order of.
But what is this? This is exactly equal to, because the way we constructed X tilde, all the copies. So this is equal to, X tilde is equal to Q times X, right. So what did we show? This implies neighborhood of X right. So it's a contradiction, this cannot happen. So if my parent graph had such a this thing, then we will always be able to find a matching that saturates this, and once we are able to find a matching that saturates it, I can always pull back and get a Q expansion. Okay. Okay, any question? This is a full proof. I mean, maybe I would have eaten a line here and there, but this is a complete proof. Okay. So this is basically a generalization of, this lemma is basically, we should view this as a generalization of Hall's theorem, a Q analog of Hall's theorem. This is basically a Q analog of Hall's theorem, right. But what I am going to prove now is something. So basically, if you notice, I do not know how many of you have seen, crown reduction is nothing but like a Hall theorem. It is basically exactly the same thing. Now I am going to prove a Q expansion lemma, which I have not yet proved. I am going to prove a Q, which is basically will be a Q analog of Hall's, of crown reduction rule. Okay, it is like a spike. Okay, and they are useful object to have. Okay, so what I am going to prove now is this. Okay, okay, this is my, maybe this is not a good. So the lemma which I am going to prove and this is what is called Q expansion lemma, okay, is the following. Let me not try to be adventurous. Okay, let Q be a positive integer. Okay, let Q be a positive integer and G be a bipartite graph with vertex bipartition AB such that A, what is the property? B is more than Q times A, B is more than Q times A. I am not saying that for every subset X subset of A this, all I am saying the size is large such that A, and secondly, let us call this first, and second, there are no isolated vertices in B. Okay, so there is no isolated, there is no degree 0 vertices in B. Every vertex in B has a neighbor in A. Okay, then what happens? Okay. B. Okay. Now, what are the conclusion? Then there exist non-empty vertex sets X subset of A and Y subset of B such that first X has Q expansion into B, no, into Y, yes, and Y has no vertex, Y has no neighbor outside X, that is, if I look at a neighborhood of Y, it is exactly equal to X or contained inside X. Okay. Furthermore, we can find these sets in polynomial time. Okay. So what does this statement say actually? Basically a statement says that look, if you give me a big enough A and big enough B, if you give me an A and B such that the side of B is at least side of QA, like large enough, and there is no isolated vertex, then what can happen is that I can find you an X here, I can find you an Y here, such that X has a Q expansion in Y. Meaning, suppose Q equal to 2, this is how it will look like. And what is an additional property is that this Y has no neighbors outside X. So, all the neighbors of Y is confined here, right. Of course, Y has no neighbor here because it is an independent set, but this does not exist. This kind of edges do not exist. X could have edges elsewhere. This we do not escape. All we are saying that the Y is this. Now, if you people remember crown decomposition, then let us look at how crown will look like. Here I have X, here I have Y. Now, if I put Q equal to 1, it has a Q expansion into Y, meaning there is a matching that saturates X into Y. So, there is a matching that saturates, and look at the remaining guy here. Here this is Vg minus X union Y. This is basically a crown decomposition. This is crown, which is an independent set. There is a head from where I have a matching that saturates into Y. This. Now, if I apply Q equal to 2, it's basically the same thing, but now basically we will have a spike like this, and this is a useful structure to have. This is exactly what it is going to be. Q equal to 3, I will have another one, right? Some another one. This is exactly how it is. The property is that this is a beautiful property is that there is no edge going from Y to this. So basically this acts as a separator between this and this. So this separates Y from the remaining, right? So this is a very good object because then all the interaction for my problem which has to happen from here to here, it has to happen via x, right, and that is a property which we exploit all the time, okay. So this is the picturesquely, this is exactly how it looks like. Look, I never said that it could be that the x which you are looking for could be equal to a for all it, right, because if B had a Q expansion from A to B, then A itself satisfies all this property, right, and clearly neighborhood of B is x because there is nothing. So I am never saying that A cannot be the candidate of x, B cannot be the candidate of y, right, but because we have weakened the condition, what do we have weakened the condition? All we are saying that look, size of B is larger and there is no isolated vertex, every vertex in B has a neighbor in A, then we will be able to find a nice decomposition of my graph into some y, x and the remaining, such that when I look from x to y, there is a nice several matching saturating x and there is no edge going from B to the remaining guy, and that is all that property it is, okay. So now let us try to prove this, okay, and then we will see how to make it algorithmic. I am not going to make it algorithmic because if you know the proof of false theorem, how to make it algorithm, this is exactly like that, okay, but we will discuss the details in a minute, okay. So now what will be the proof strategy? Let us try to think of a proof strategy. Do you see an algorithm for, say for example, do you see a kernel for vertex cover of size 3k using this? No, yes, no? It seems everybody just sleeps in the class. Okay. How many you know the definition of vertex cover? You know the definition of vertex cover? Do you know the definition of vertex cover? So let me teach you how to apply this first. Here's my tool. Vertex cover, okay. If there is an isolated vertex, delete. Agreed? No need, okay. Find a maximal matching greedily. Okay, find a maximal matching greedily. Say M. So now I am going to prove you a small lemma. Okay, if vertex set of G, okay, let G be a graph, then in polytime I am going to do three things, okay. A, is less than 3k, that I can conclude, or B, I can conclude, or B, find a decomposition like this into, let us call it y, x and r. So this is like remaining vertices, okay, or find a decomposition into y, x, r, or C, conclude that G comma k is a no instance for vertex cover. Okay, I want to conclude this. So what my algorithm does? It does nothing. It starts with finding a maximal matching. M is a maximal matching. I can find this in greedy polynomial time, right? Now, so no, first if the number of vertex is 3k, it does nothing. It says just take it, I don't care. If the number of vertex itself is less than 3k, then I don't do anything. I say take this, that's your kernel. Because number of vertex in the graph itself is small, I don't want to do anything. But suppose, so now we are in the condition when Vg is strictly more than 3k. So now what I do, I find a maximal matching. Now I check, is the matching more than k? If matching is more than k, what can you say? So suppose there are k plus 1 size matching edges. Can you have a vertex cover of size k? No, because every vertex cover must pick at least one. So this is a no, so then you return that gk is no. So now we know is less than k. So now I find, so now I make a decomposition as such. One side I put vertex set of m, and the remaining, what is this? Is there an edge here? No, m was a maximal matching, maximal. So if there was an edge, I would have greedily put there. So I is an independent set. So now forget the edges between inside Vm. Okay? Now you apply your theorem, apply your decomposition, right? You apply your decomposition, right? Because these guys, so all the edges, all the neighbors this guy had is present in this graph, in the graph which only edges which I have deleted is this edges, right? Now if I apply this, so what will say? If this guy is more than, oh, I shouldn't say, no, this will only tell you, okay, my bad, let's call it 4k, okay? Why? I will tell you why. Because what does theorem tells us? Now what is the size of V of m? 2k. If my A is, because now Q is 1, if the size of I is more than 2k, then what will, it will find me such object, decomposition. Because if there are k edges, how many endpoints are there? 2k endpoints are possible, right? Because this is vertex set of m, right? So this could be as bad as 2k, right? So now if I want to apply this theorem, and there are no isolated vertex because we have been deleting all the isolated vertex, so everybody in I has a neighbor here. Now if I apply my lemma with q equal to 1, what I am going to get? I am going to get a set from here, a set from here, so that there is a matching that saturates it and all the neighbors are here. And now you can prove to yourself there always exists an optimum solution for vertex cover which contains whole of y, always. Why? Because look, there is a matching which saturates it, right? There is a matching. So any minimum vertex cover must contain either this must contain one vertex from each of this matching edges. So basically you can show that if it contains this, just push it to here. So then you have still maintained the same size, but now you are able to cover all the vertices here and maybe more, and you can prove this formally, right? So your reduction rule will be take y, take x into your solution and decrease your parameter by k minus mod x, because now in the remaining graph you are looking for a smaller solution. So you keep applying this. When will you stop? When the number of vertex becomes less than or equal to 4k. Say, because we delete isolated vertex, if the graph is too large, I will apply again, either I will be able to say no or I will find decomposition. If I find decomposition, I apply my reduction rule and I am done, right? So this will give you a 4k kernel, and if you do slightly what I call massaging, then you will get 3k, but I am not going there, that is not the objective, okay? So this is just one application of this nice theorem, but let us prove this now, okay? This was just a, what is that called, teaser. Okay, so now how are we going to prove this theorem? We are going to prove this theorem using induction on side of A, okay? So proved induction on side of A. If A is 1, are we done? Suppose this is 1, and how my graph looks like? I have a singleton and number of neighbors it has here, how many? Greater than q. then there exists a non-empty vertex set X subset of A and Y subset of B such that blah blah happens. So my at this point of time my A itself is X and my B itself is Y for singleton. So by induction holds, right? In induction we are able to find a Q expansion because it is a Q star. So all good. Okay. So now okay. So now we are in a general condition. We have A and we have B. So what did we previously prove the lemma? We previously proved a lemma. What did it say? That if for every subset here, it has, what did the previous statement said? If for all X subset of A, neighborhood of X is greater than Q times X, then there is a Q expansion from A into B. This is what we said, right? This is what we proved last time. So I apply this theorem. If this happens, we are done, because then I will return, if already this property holds, then we are already great, we are done, we are dusted, okay. The worst case happens, this property is not satisfied. It means I am going to find an X, right, and a Y with certain properties. So let us look at how does it look like then, okay. We are done actually, there is nothing more after this. Okay. So I found X, okay, let us look at, here is my X, here is my n of X, okay, and what is this? A minus X, and what is this? B minus n of X, okay, and we know why X cannot be equal to A. Let us ask ourselves, why X cannot be equal to A? What is the corollary? What is by B saying? That if this condition does not hold, what is the contrapositive? There exists X such that neighborhood of X is strictly Q times X, right? So if this theorem does not hold, the X which is returned by my algorithm cannot be equal to A, because what we know about because that is where we are using the fact that the size of B is more than Q times size of this. So I cannot, this algorithm, the violating set X cannot be equal to A. So this is non-empty. So A minus X, this is non-empty, right. So what did we conclude? X cannot be equal to A, else we contradict that, that cardinality of B is greater than or equal to Q times A. Agreed? Okay, but what is the property of n of X? It is strictly less than Q times X. So now what property did B had? B had the property that it was Q times A. Now I have removed maybe some 10 vertex, but suppose Q is 3, but I have removed less than 30 vertices. So what I want to show is that B minus n of X is also greater than or equal to Q times A minus X, because I want to apply induction hypothesis, right. But hey, everybody here was, think of this way, that everybody was trying to have look at their Q people, but collectively here there is less than Q into X people. So of course the size is actually larger than the Q times this, right. So this happens. Now there is a question of, but I cannot still apply my statement. Let be a bipartite graph with vertex bipartition such that this is true. Second is there are no isolated vertex. Why can't I have a, because I deleted x, why can't I have a vertex which becomes isolated? But why did it become isolated? It means the guy had a neighbor to x, right? But all the neighborhood of x is here, right? So again, so what is this? No isolated vertex. Okay, so now we definitely have A whose size is strictly smaller and it satisfies all the premises of my lemma. So now I can apply induction hypothesis. Okay, great. So what does induction hypothesis tells us? By induction hypothesis, there exists some x star, some y star, such that, what is the property? Such that x star has a q expansion into y star and all the neighborhood of y star. So what is this? There exists q expansion from x star to y star and n of y star is contained inside x star. By our induction hypothesis, clearly the neighborhood of y star is contained inside x star. But why can't y have a neighbor in x? That is because a vertex in y star is not in neighborhood of x. So actually the set which you found here is also a set in my original graph, right? Because we have to prove the things in the original graph. So whatever x star and y star I find in this smaller graph is also a expansion set in my original graph, right? So I am done. Okay, so this is what the proof is. This is it. There is no more magic here. Okay, so this is the end of the proof. Okay, okay. Why it is an algorithmic proof? Well, all I am applying is induction. And how did this proof work? Basically, we transformed into a G tilde graph and we were applying Hall's theorem there, right? So what I will do? I have to find this set, I will take my G, I will make G tilde graph. I will apply my Hall's theorem. For that, for which there is a proof that in polynomial time either it will give you a matching saturating this or it will give you a violating set. Find. If it gave me a violating set, right? If it gave me a violating set, then what do I do? If it gave me expansion in G tilde, then I return you expansion. If it gave me a violating set, then I delete it and inductively apply on this, and that's it. I will not apply this procedure more than polynomial time. So if there is a polynomial version of Hall's theorem, polynomial time version of Hall's theorem, which does the following, either finds a matching saturating one side or gives me the violating set, we are done. So all we need is an algorithm to do that, which I hope has already been covered when someone was teaching you ground reduction. Okay, so I'm going to use that as a black box. So if there is an algorithm for that, there is an algorithm to find my own sets. Okay, okay. So now I have 15 minutes, okay, and I definitely cannot teach you the kernel for feedback vertex set in 15 minutes. It's impossible. I will not even attempt. Okay, so let's try to do, not that I recall very well, but let's try to do component order connectivity. Okay, maybe 15 minutes could suffice to give you some feel of this. Okay, so let's rub everything except the statement of the theorem. Okay, is the proof clear to you? Okay, let's try. Not that I have worked out, but let's see. So the problem is, so it is called L component order connectivity. Okay. Okay. So basically, I have G, K, Okay, question is, does there exist S subset of Vg such that mod S is less than or equal to K, and every connected component of G minus S has size at most L. Okay, every connected component of G minus S has size at most L. So what is one COC? It's vertex cover. One connected order connectivity is a vertex cover. You delete, you get isolated vertex, right, or independent set. So every connected component is singleton, has size 1. Now I am allowing you to have size at most L. Okay, okay. So how do we so what will be a trivial approximation algorithm for this? Right? Look, I find a connected component of size L plus 1. If I have a connected component of size L plus 1, then I have to delete one vertex, no? So find a connected component of size L plus 1, delete, because at least 1. So this will give you a factor L plus 1 approximation algorithm, right? So for example, basically, and how we can find, I mean there are many ways of finding it, okay? Find a connected component of size L plus 1 and delete. Okay, you keep deleting it, right? So every time you are finding a connected, like do brute force anything, but there are many ways of doing it, but let's for now suppose you are able to find it somehow. So basically what are you doing? You are deleting some L plus 1 size spanning trees basically. There could be edges here, so I am deleting. Now the point is, look, since I am only looking for a connected components of size at most L, these guys together cannot be there. So at least one of these vertices must be in every solution. Every optimum, approximate, every solution, one of these vertices will be there. So I just keep doing this greedily, okay. So let's S star be the set of vertices returned, right. What we know, there are L plus 1 guys and at least one guy must go in the solution. So now I will check if S star has size more than L plus 1 into K, what can you say? This is a no instance, right, because I have a L plus 1 witness, K plus 1 witness from which are disjoint. It is same thing as you have a K plus 1 matching, right. You have to pick one vertex from each of this matching edges. And so if you have K plus 1, you at least need K plus 1 in your budget. And if I have found K plus 1, L plus 1 size disjoint connected components, then I have found no instance. So if S star is this, return no, right, good. So what do we know now? So S star is less than or equal to L plus 1 into K. So now let's look at this is my S star and this is my remaining guys, okay. Here I have a small component, okay, I have a small component, okay, that's fine. And now I want to apply my expansion lemma to get some decomposition and prove a statement like vertex cover, okay. Okay, so let's see if we apply with, let's apply L expansion lemma. Let's apply L expansion lemma, then what happens? Okay, notice here that all these vertices which this is connected component, this is a vertice in S star. right? Okay, I don't know what. Okay, so let's apply with some X star expansion. We'll fix that. Okay, we'll apply some X star expansion. Okay, and what is the basic reduction rule? If there is a connected component of size at most L, delete it. Basic reduction rule is if there is a connected component of size at most L, delete it, because why want to delete anything from here, right? So the basic reduction rule, if there exists a connected component of size at most L, delete it. We will keep applying this whenever the requirement is, because this is no use putting any vertex from this in the solution. Okay, now let's apply some X star expansion, whatever. Okay, so to apply X star expansion, the size of this has to be more than, let's call this Y, no, let's call this B. Size of the B has to be more than X star times size of S star. If it is more than this, then we are able to apply this lemma, whatever it is, right? Okay, so now we will fix X star. I don't know what is X star at this point of time. I want to argue that if we have such a partition, then we should be picking all this guy and putting them into the solution. This is what my idea is. Okay. Okay. I hope by now you have heard the statement of this lemma several times, so I can drop this. So what we get? We will get. So what are we going to get? We are going to get X here, Y here, and there is every vertex here. Suppose there is, and the remaining guys here, right? Right. And what I will do here now, look, but to apply this rule, I needed to have a bipartite graph, right? I needed to have a bipartite graph. From where did I get bipartite graph? Okay. So what I am going to do is take each of this component and consider them as a singleton vertex. Okay, they are singleton vertex. So you contracted them. So now to apply this, that automatically means that I have to apply an extra L here, because now each vertex could be as bad as size L, right? So basically my expansion is going to be some X star into L expansion, whatever that means. Okay, we'll worry about this. I mean, this is, look. Okay, so now we have this. I want to say that every vertex in X must go into the solution. When can I say this? What catastrophe happens if I do not pick every vertex in X? What catastrophe can happen? Look, this guy, when can I say this? Look, this guy is neighbor to lots of people. Suppose X star was L, X star was L. So what does this means? This vertex is neighbor to how many people? L square people, right? This guy is neighbor to L square people, right? L square people. This guy is neighbor to L square people. Each of these guys has at least one vertex, right? Now, so basically I can make, starting from here, like just take this first L guys, right? I mean, I can do, this is one connected component of size, how much? L plus 1, at least L plus 1, because if I have taken here L and I put this guy in, it's L plus 1, right? Now, okay, so if I have applied L square expansion, I have applied L square expansion, so I can at least make right? So this guy is common to at least L more objects. So if I don't pick this guy, I need to pick at least L more vertex into my solution. At least L more vertex into my solution. Okay? Okay, now, okay, but that, does that mean, what I want to show? I want to prove to you that G minus X, once I delete X, every component here has a size at most L, so my stupid reduction rule will apply and they will go away. I want to show, so G comma K, if and only if this happens. This is what my objective is, this is what my goal is, okay? Okay, what should I apply with? Okay, fine. This is what I would like to show. Okay, for backward direction it's trivial. If I have a, for this I have a solution of size k minus mod x, then I pick x, then that is definitely a solution for everything else. So this direction is obvious. What is not obvious is the forward direction, right? What expansion should be applied that I can say for sure that, hey, if you have a solution here, then there always exists an optimum solution which contains all of these guys. Okay. Now, what happens when, look at your optimum solution, it didn't pick every vertex from here. So what did it do? It picked, if it picked every vertex from here, then there is nothing to show. So what happens that it left some guy, but it picked some people here, right? So let's just try to look, if this would have been a singleton, this is still easy to, trivial to show. Now what I am trying to tell you, but look, this is why fine, okay, it is enough for me, okay, so suppose I have just applied with X, with L expansion, okay, I have applied L expansion or say L plus 1 expansion. If I apply L plus 1 expansion, look at this guy, you must be picking some vertex from here, right? I am telling you move this to this guy, that is all that I am saying, because this guy is adjacent to L plus 1 component, I do not know the sizes, this is why, otherwise if I knew, then I will do something very differently, okay. So what I am going to do, apply, I am going to fix X star as L, X star, now what is my B? B is where every guy is condensed to singletons, this is the graph I am looking for, this is where I am applying my expansion, okay. So I am applying my L expansion into this, I got this, my claim to you is that, hey, I do not know about the sizes, then there always exists an optimum solution containing X. Why? Suppose you picked, so if you did not pick a vertex in X, you must have picked some vertex here, because look at this guy, it is definitely a connected component of size L plus 1, because there is a L here, there is a L guys here and this guy, and each of them must be containing at least one vertex, right? It could contain as many as L vertex, then you might be needing much more vertex from here, right? So at least if I look at locally here, I have L plus 1 vertex. So look at this, local packing, here this is L plus 1, this is L plus 1, right? L plus 1 at least, if I look at this and look at the connected component together, then this is an L plus, strictly greater than equal to L plus 1 size connected component in my original graph. So is this, okay. It means in each of them I must be picking at least one vertex into my solution, right? Let's call them, let's denote them at least X, maybe more, but at least X, okay. So suppose I have a solution S, okay, I'm going to do delete S minus X union Y and add X, this is my new S prime. I have deleted everything from X union Y, I have deleted any vertex we have picked and I have added X, okay. My claim is first of all that size of S prime is less than equal to size of S prime is less than equal to size of S. Is that clear to you? Why? Because I have deleted everything. So I have at least deleted x many people. I have at least, because from each of them I must be deleting at least one vertex, right? Either this or maybe someone from the top. So when I delete this, I have definitely deleted cardinality of x number of vertices, right? Maybe more, but I have definitely deleted cardinality of x vertices. And now I have added back all the vertices of x. So size of S prime cannot be larger than the size of my, and remaining things I have not changed. So now what you have done, you may have solution here and you have picked up everything else. I'm going to claim to you that S prime is also a solution for my problem, because delete everything else, right? Now the only problem which could have happened is here, but here there cannot be any problem, right? And so look at any connected component. Any connected component could completely live here, could completely live here, and could live like this. Now if I have deleted this, the guy who were completely living here and size at most L, it is still size at most L because I have not deleted anything else. Anything which was living like this, I have deleted their middle part, so it can only become smaller. And someone who was living completely here, because I have deleted everything from here, they were anyway size at most L. So S prime is also a solution where everything here is part of it. So then, like a vertex cover, what is my reduction rule? I will apply this, right, with L being my this, and do this. But what is the size? Okay, but what is the size of B? Size of B is, so when everything stops, my B is at most L times S star. But B, each vertex in B might be meaning a L sized vertex. So real size of B, so size of my graph when we completely stop, my A S star has size how much? K into L plus 1, right? So that's your S star. And size of B is K into L plus 1 times L for the expansion times the size of each guy, another L. So basically this is a kernel of size order LQ times Q. Okay, so what did we get? We get a kernel of size order LQ times K by applying L expansion, right? And this is very non-trivial. This was not known till very long time. And but look, we have lost at several places here. Where are we lost? We lost because we didn't know the sizes of these guys. Okay, so the very simple way to go from LQ to say something like L log L into K is following. So you group these components into powers of 2. So all those which are 2 power 0 and 2 power 1, 2 power 0, then 2 power I plus 1, between strictly less than this, 2 power I plus 1 and this, right? And each range you apply appropriate, because you know you do not have to, because here what I am saying that, like maybe, so for example, if already this component had size L, then if I put this guy with singleton with only one expansion, it has become a component of size L plus 1, right? Because only thing which I use in argument that, hey, I have a witness here from where you must be picking one vertex, and the witness was a connected component of size greater or equal to L plus 1. So if I knew this guy itself is L size connected component, then I put together this is already a L plus 1 size connected component. So from here itself you must be picking one vertex. So when you divide, when you group these connected components based on their sizes, okay, between 2 power 0 to 2 power 1, 2 power strictly less than 2 power 1, 2 power 1 to strictly less than 2 power 2, and 2 power log L, because 2 power log L is L. And now in each you apply different. You will apply, because look at L by 2, then I will apply 2 expansion. If look at all the connected component which has size at least L by 2, then I will be applying 2 expansion there, because for every 2 expansion I know that if I take 2, its size is more than L, right? And then you can reduce the kernel size. So like you have to apply some brain, and actually you can get rid of this, but that requires much more hard work, and then that requires a weighted form of expansion lemma. And if you do, and on top of weighted form of expansion lemma, if you apply linear programming, then you can get a kernel of size 2LK or I think 6LK, but that requires much more hard work, and that's a paper in IPEC 2016. So with this, at least I will stop for today, and tomorrow I will give you a kernel for feedback vertex set. So we'll start and we'll try to utilize this algorithm. If you do not know if you do not know constant factor approximation algorithm, it might be a good idea for you to at least browse through. Okay? Okay, thanks.